Hi, my report is about Minister for ML, and this report is intended to readers who are new both machine learning and TensorFlow. If you already know business and what the softmax response is, you might prefer this faster proceeded report. Be sure install TensorFlow before starting other tools. Um, Means is a simple computer vision data set. It consists of image of handwritings, digital like the screen displayed 5041, and it also includes labels for each image, telling us which detail it is. For example, the labels for the above image are 502, 4 and 1. In this report, we are going to train a model to look at image and predict what digital they are. Our goal isn't to train a real model and achieve state-of-the-art performance, but rather to dip a tone into using TensorFlow. As such, we are going start with a simple model called a softmax Linux. And uh, the master data is based on Yonkin website. If you are copying and pasting in the code from this report, start here with two lines of code which will download and read in the data automatically. And the main data is split into three parts: 55,000 data points of training data, 10,000 points of test data, and 5,000 points of validation data. This split is very important. It's necessary in machine learning that uh, we have separate data which we don't learn from. As mentioned before, every means the data points have two parts: an image of handwriting detail and a cross from labels. Um, we call image X and label Y. In both training sets and the test set contains image and their corresponding labels. For example, training bounce. Each image is 28 pixels, multiple 28 pixels. We can interpret this as a big area of numbers. We can flat this area into a convert 28 multiple 128 to equal 784 numbers. It doesn't matter how we find an area as long as we are considerable between images. Flattening data through away information about 2D structure of image. Well, the best computer vision method to explore this structure, and we will in later report. But the simple method we will be using here, software regression. The result in this means is a tensor with a shape. This first dimension is an index into list of images, and the second dimension is the index for each pixel, each image. Each entry in the tensor is a pixel intensity between 0 and 1 for a picture pixel in particular image. Each image has a corresponding label, a number between 0 and 9 representing the digit drawn in the image. And each image has for the purpose of this report, we are going to want our label at one hot vectors. A one hot vector is vector which is 0 in most dimensions and 1 in a single dimensions. In this case, the nth digit will represent as a vector which is 1 in nth dimension. For example, 3 will be 0, 0, 0, 1 and 0, 0, 0, 0, 0. So the next, we know that every image in Mint is of a handwritten digital between 0 and 9, so that there are 10 possibilities things that give a given image can be. We want to be able to look at an image and give the probabilities for each it being each digital. For example, our model might like a picture of 9 and be 80% sure it's a 9, but give a 5% chance to it being an 8, and a bit of a probability to all the others because it's not 100% sure. This is a classical case where a softmax region is a natural simple model. If you want to assign a possibility to an object being one of several different things, softmax is the thing to do because softmax gives us a list of values between 0 and 1 and add up to 1. Even later on, when we train more sophisticated models, the final step will be a layer of softmax. A softmax regression has 2 steps. First, we add up evidence of our input being certain classes, and then we convert our evidence into possibilities. And you can picture our softmax regression looking something look the following, like the first picture. Although with a lot of more axes for each output, we compute a weighted sum of axes at a basis and apply softmax. And if we write out as equations, we get the second picture. And to do efficiency numbers computing in Python, we typically use libraries like NumPy that do expensive operations such as matrix multiplication outside Python. Using highly efficiency code implemented in another language. And however, they can still be a lot overhead from switching back to Python every operation. And this overhead is especially bad if you want to run a computation on a GPS or in a distributed manner, where there can be a high cost to transferring data. We describe this increasing options by multiplying symbolic variables. Uh, let's create one like the first. And here the y isn't a special value; it's a placeholder, a value that we will put when we ask TensorFlow to run a computation. We want to be able to input any number of mixed images, and each float onto 784 dimension vectors. We present this as a 2D tensor of the following points numbers with a shape 9 and 784. Alright, let's go to know where we can predict correct labels. TF argmax is a very useful function which gives an index of maximum of the tensor of the along the axis. And we also need the weights and basis for our model. We can image treating this like additional input, but for TensorFlow has an even better way to handle it. And then load the means the data. If you could copy and paste the code in this report, start with these 2 lines of code, and the code will be automatically downloaded and read into the data. And then the common usage of the TensorFlow program is to create a graph first and then start it in season. It allows you to cross the operation to build a run diagram of the calculation. And now we know define weight for our model W and deviation of B. We can think of this as actual inputs, but TensorFlow has a better way to deal with them variables. And we will be the vector of the input images x and multiple weights and matrix W plus the dimensions of B. TensorFlow in this line is actually added into a calculation of new operations. These operations include the calculation of the gradient, the calculation of the parameter update step, and the application of parameter update step. The return of the operation training step will be updated with the granted descent for the parameter application at runtime. Therefore, the training model can be completed by repeating the calculation of train step. And getting 92% on missed is not good. It's most embarrassing to be bad. And 3.7 also applied a wide of flexible conversion and poor operations. How do we that? In this example, we also choose the vanilla versions. And in order to apply this layer, we first reform the 4D to the X tensor, where the sensor third dimensions correspond to this with the height. And in the end, we add a layer just like the one of the first of the softmax regressions, and we add log records to each 100th atom during the training of. And thank you.